Okay. Hey guys, I am going to go ahead and go through lesson 15 with you. Here we go. Should have full screen now. This will be our online asynchronous course to make up for the time that we lost due to Hurricane Milton. Thank you, Milton. And we're going to be talking about Callister Chapter 9, phase diagrams. And you guys will remember the funny, not funny GIF, or not GIF, meme of Pikachu in the binary eutectic phase diagram. I'm gonna like hover over here for a second so you can see the lesson objectives. And here we go. Okay, phase diagrams. A phase diagram is just um, a diagram that we can use to determine the concentrations at certain temperatures, or rather the phases present at certain temperatures and certain concentrations for a usually two or more types of materials that are mixing together. These are most commonly metal alloys. And you'll see here on the top of the graph, you have a liquid. There's a liquidous line that runs along the bottom of the liquid. And then on the bottom end, you have a solid, which we're referring to as the alpha phase, or A. Uh, these slides, it just looks like a typical A, but this is alpha. Usually it's a Greek letter, alpha, beta, gamma, zeta, epsilon, blah, blah, blah. So you have a liquidous line and a solidus line. Okay. Between these two, you have a nicely like sandwiched region where you have liquid and alpha phase. So this is a liquid with solid globules or solid pieces that are kind of floating around in your liquid. All right, so here, this is also called an isomorphous binary phase diagram. It's binary because we have two components that we're talking about. This is copper and nickel. So you'll notice on the x-axis, you have 0 to 100% nickel. What that means is if I'm down at 80% nickel, I have 20% copper. So along this line on the left, that would be the y-axis line. At x0, you have 100% copper. And then on the opposite end of the spectrum, at 100% nickel, are you at 100% net weight percent nickel, you have 100% nickel. So everything in between is a mixture of the two. So that's why this chart exists. So it's binary because you have two types of components. And it's isomorphous, which means that you have complete solubility of one component into another. So your alpha phase, this FCC solid solution that we have, is one. It covers all the way from the very beginning all the way to the very end. It's 100% solubility, which is not true for all materials. It's not true for many materials, I should say. Okay, so when we say solution, we mean a solid, liquid, or gas solution, or a single phase. And a mixture just means that we have more than one phase present. There's a solubility limit with most materials, and that is the maximum concentration for which there exists only a single phase. So this is a very common example, sugar water phase diagram. So I think all of you have done this before. Most likely when you're making lemonade or something like that. What you find is if you put too much sugar into cold water, there is a point at which it will stop dissolving in the water. And you're going to end up having water with some you're going to have water with some like sugar crystals floating around in there. And that's what you see here at around 20 degrees Celsius. Let's say I'm 20 degrees Celsius, which is room temperature, and I move over. Actually, I'm going to pause this real quick to make sure. Oh, actually, no, I have a laser pointer. Cool. Okay. where we're fixed now. Okay, so at 20 degrees Celsius, if I draw this line here, what I find is that I add sugar and add sugar and add sugar, and I'm just, it's dissolving freely. Then when I hit this line, I am now entering a regime where the sugar is no longer dissolving in the water, and I have sugar and water together. Even though that liquid, we're calling it liquid, we're not calling it liquid water because it's actually this liquid solution, this liquid syrup solution. But it's liquid syrup solution plus solid sugar. And then, and as all of you probably know from your freshman chemistry course, if you're like right here at 70%, let's say 78% sugar, if you start heating up that water and bring it up to let's see what 70 degrees Celsius, you actually your all of your sugar will then dissolve. And we all know what happens when you cool the water back down. If you let it set out, it'll go back under this, and you'll start to have what's called a precipitation of the sugar floating back to the bottom of the beaker. So here's a very simple sugar-water phase diagram. So the question here is, what is the solubility limit for sugar and water at 20 degrees Celsius? And so, just like I was talking about earlier, you just draw a straight line from 20 to that point, bring it down, and it's around 65. 65 weight percent sugar. At 20 degrees Celsius, if concentration is less than 65%, you've got syrup. And if it's greater than 65%, you have syrup plus sugar. Okay, so you have components and phases. The elements or compounds which are present in the alloy are the components. So that would be, for example, aluminum and copper. Of course, we've been talking about copper and nickel all this time. This one is a copper nickel system. So those are your components present. The phases are the physically and chemically distinct material regions that form, and they've got this nice little picture here. So you have a beta phase, which is the lighter, kind of nicely colored one with the little lines through it, which is interesting. And then you have alpha phase here, which is the darker phase. So this is an example of a solid object, and I think this would be referred to as perlite. But this is your aluminum copper alloy. So altering your temperature can change the number of phases present, which I think I also just talked about. And what we're doing here is we're literally just drawing a path from A to B. Once you heat up the water, you'll start to get a precipitation. At 100 degrees Celsius, that's when water starts to boil. So you'll actually start getting water gas in your thing as well. But that's why this ends at 100, because it stops being true. And then, so yeah. So what we're saying here is either altering temperature or altering your composition, or I'm sorry, altering your concentration total can change the phases that you have present. So really, you have the power as engineers to drive your system to wherever you want on each of these charts, is the idea, by either adding to, taking away, or adjusting the temperature. And we will remember, this is just a callback to one of our previous chapters where we talked about the Hume-Rothery rules. This is a question of how do we know if we can dissolve one metal into another metal specifically, and that is using the Hume-Rothery rules. So mainly looking at crystal structure, electronegativity, and the relative radius. Okay, so if we know temperature and composition, then we know which phases are present, right? That's rule number one. So at 1100 degrees Celsius and 68%, we're going to have just our alpha phase, right? And then at 1250 degrees Celsius and 35 weight percent nickel, we're going to have both liquid and alpha. The problem is we don't really know what the concentration of just our liquid and alpha phase in this particular instance are. So if we know temperature and concentration, then we can determine the composition of each phase, right? So you'll notice this picture is a zoomed in version of this picture right here. So we're at this one where there's a much wider gap. We've just zoomed in. We're between 20 and 50 and what is that, 1100 to 1500 degrees Celsius. But what we're going to do is we're going to pick a point and then we're going to draw what's called a tie line. So we have 35 weight percent concentration of nickel. Well, and I guess we're going to start over here. And we only have liquid present here. So we know the concentration of the liquid because all we have to do is, since there's only one phase present, we stick our point where we want it at 35 weight percent and at our temperature of 1320 here. And we know that our concentration of the liquid is 35 weight percent nickel. At 1190, which is down here, we also know it's still 35 weight percent nickel because we're still along this straight line, right? So if you're in a single phase region, all you have to do is draw your line straight down to our weight percent nickel axis, and you will get whatever the composition of that specific phase is, right? So it gets more complicated when we go to 1250 degrees Celsius and we have both liquid and alpha phases present. That's where we get our tie line. So I'm going to play this again so you get an idea of it. So we start at B, point B. We're going to draw a straight line horizontally that connects our liquidus and solidus lines, right? So that we draw that line. Here we go. Boop, boop. Then what we're going to do is we're going to draw straight lines down to our x-axis, right? And then we get the compositions of each phase. So here at our liquidus line, we can get the composition of our liquid region, which is 32 weight percent nickel. So then the opposite of that would be 68 weight percent copper, right? And then on the other side, if we draw our solidus line straight down, or from our solidus line at the tie line straight down, we get 43 weight percent nickel. And then the opposite of that would be, let's see, is that 57 weight percent copper. Okay, and then I guess we're just doing that. So if we know temperature and composition, we can determine the weight fraction of each phase. Okay, so this is a little bit different. So right here, we were talking about the phase compositions, right? Now we're going to talk about weight fractions. We can actually find the weight fractions. Remember, towards the beginning of the semester, we talked about weight fractions. So we're going to discuss that for a minute. So at temperature A, there's only a liquid phase present. So the weight fraction of liquid is 1.0. The weight fraction of alpha is 0. And down here, it's the opposite. Our weight fraction of the alpha phase is 1.0, and the weight fraction of liquid phase is 0 because we have no liquid present down here, just alpha. Up here, we've got liquid and no alpha. Now, we can actually determine at our new point B what the weight fractions of liquid and solid phases are. So this is that amount that we were talking about in our last class. How much liquid versus solid do we have? I didn't really cover this because I was trying to move us through so we could discuss chapter 10. But you can find the weight fraction. All you have to do is take the compositions present. So it's going to be your solid. So this line here, 43 minus 35. Look at this line. So we're doing 43 minus your point that you're at, minus 35, divided by R plus S, which is going to be this line plus that line. That ends up being 43 minus 32, because that's just going to be 43 here minus all the way down here, 32, right? And that's how you get 0.73. And that's your weight, that's your mass fraction of liquid. So how much solid do you have at this point? Well, it's going to be the opposite of that, right? So it's going to be 27, 0.27. And that's what they do down here. They just kind of invert it. There's it's instead of S over R plus S, it's R over R plus S, and then you get your weight fraction of alpha. But it's also just the inverse of this, right? So your tie line connects the phases in equilibrium with each other. This is also sometimes called an isotherm. And what is the fraction of each phase? So we're going to use the lever rule here. You'll remember from statics that if you have a mass sitting at a distance away from a fulcrum, then it is force times distance that equals your moment, right? You're generating a moment around this. So you might have a smaller mass on this end of your teeter-totter, but on that end you've got a larger mass. But the smaller mass is actually farther away. So these end up equaling out, right? And using the equations that you would typically use for this, you can actually find the mass fraction of each phase, which is another way of thinking about it. So m alpha times s, boop, boop, is equal to mass of liquid times r, boop, boop. And then using this relationship, you can actually find each one knowing S and R. And then you can just generate these relationships, and you can bring it back to specific compositions as well. So that's why these exist. Okay, so we're going to go through an example real quick. Cooling of a copper nickel alloy. So we have a phase diagram of our copper nickel system that we know and love. We're going to consider the microstructural changes that accompany the cooling of a copper nickel alloy that's at 35 weight% nickel. So here we go. And as we cool down, here's what happens. As we get down to our our liquidus line right here, we actually start to form these little tiny granules, little tiny nuclei, also called seeds. And these are our alpha phase seeds that are forming inside of our liquid phase, right? So little alpha phases that are surrounded almost entirely by liquid phase. And you can actually calculate the weight% of each phase at this point, right? Because at this point, you're actually drawing that tie line all the way up to 46% right here. Okay. As we continue to cool down, what happens is these little grains start to get bigger and bigger. And you'll notice the concentrations of nickel start to change as well. So we're getting little, bigger grains. Finally, at this point, we now have very large grains forming that are kind of precipitating, at the bottom of our liquid mixture. We can calculate the concentrations. And then finally, once we get into our solid phase, we now have these. And the best thing to kind of, we're talking about really, really high temperatures, like 1200 degrees Celsius. I mean, that's extremely hot. So we're literally forming metal here. We're starting from molten metal, volcano style stuff, and we're actually cooling it down, and we're getting grains out of this. Depending on how fast we cool this system, it will change the shape of these grains. So you do end up having things what's referred to as chord versus equilibrium structures. If you have a really slow rate of cooling, then you get an equilibrium structure. So you get kind of a nice, a nice uniform concentration blob of material that is pretty similar. But if you have a really fast rate of cooling, you end up getting a chord structure. So first, you have your first alpha to solidify. Then as it continues to cool down, it solidifies outward. And this isn't what you end up getting. And you'll notice that your concentration in the middle is actually similar to or not similar, but different from your concentration on the outside. Compare that to the slowly cooled structure. And what you have is basically just a uniform 35 weight%. Everything's the same. Over here, it's different. Your concentration on the outside is actually higher concentration nickel. Or I'm sorry, your concentration on the inside is higher, but your concentration of nickel on the outside is lower. So it's just something interesting to note. So, when we talk about quenching, for example, this will happen in quenching. You're going to end up having a higher concentration of one of your two materials on the outside, depending on what is dissolving and what. It depends on which one I think has the lower Um, which one has the higher of the two melting temperatures? So the reason we want to talk about this in general is because this has a direct effect on your tensile strength. So depending on your concentration, you will have different tensile strength and different ductilities. Um, so copper nickel that we know and love from 0 to 100%, your tensile strength will go up and then it'll hit a peak. It'll hit a peak at around 68%, and then it'll go back down, to here. So what's really cool about this is that your tensile strength for pure copper is really, really low. Your tensile strength for pure nickel is much higher, but still low. But if you get into that sweet spot right in between at around 68%, you will have a really high tensile strength, higher than any of the two, or higher than both of the others, individually. And perhaps even higher than both of them combined. I think so, yeah. So that's really cool. Like that's actually very significant. But there's always a trade-off. You always have to pay for whatever cool thing you get. So with ductility, you actually see an inverse curve. So at that same around 68%, it actually hits its minimum ductility, right? Now, what's cool about this for us engineers, specifically for material scientists, but for engineers in general, is that it means we can really tailor this to what we need, right? So let's say I really need something that has a tensile strength of 400 megapascals or between 400 and 300, let's say. So it's got to be in this range. That's acceptable for me, at least 300. But I need a ductility that is, let's see, that would be between 15 and 40. So if I look over here, 15 and 40, then what kind of ductility can I get? Well, if I need that ductility really low, maybe 35, I know where to go, and I can get what I need from both of those ends. Okay, so now we're moving on from our uh, isomorphous systems into our binary eutectic systems. Okay. Um, so binary means you have two components, and eutectic means that it has a special composition with a minimum melting temperature. Right here, that's your eutectic point. It means that on this curve, we got weight percent silver. This is a copper silver system. Yep. So we're going from 0 to 100% copper. So what it means is there's a special mixing that I can do here to get a melting temperature that is lower than either end. So it will actually melt at a lower temperature, which is really fun. Um, there's a lot of things that, you can do with that. Garrett was mentioning something about how solder is specifically mixed together to achieve this lower melting temperature, and I can believe that. I haven't looked into it personally, but I do believe it. Um, maybe somebody should double check it. But um, it's really cool that you can get this feature, right? And as it happens in material science, specifically with alloys, this is an extremely important thing. Um, and also, once you see it, you can't unsee it. You see the little Pikachu ears coming out, right? Pikachu ears. So it's Pikachu, and he's show it because it's funny. It's not really that funny, but it's worth showing again because it reminds us how to make a binary eutectic phase diagram. There's Pikachu. He's got his ears, and then he's got his alpha phase, his liquid, his beta phase, and then one ear is beta plus liquid. The other ear is alpha plus liquid, and then in between we have alpha plus beta underneath that eutectic point, right? Bling. Binary eutectic. Okay, so we have three single phase regions. We've got our alpha, we have our liquid, and we have our beta over here. You'll notice that the alpha and the beta regions are very, very small. That's okay. We can have that sometimes. In some cases, like in steel, we have a little tiny sliver of a phase. So that happens sometimes. Limited solubility. So alpha is going to end up being mostly copper. beta is going to end up being mostly silver. That's just how it works. You're not going to have beta with a really high amount of copper in it. It's just not going to happen. And then you have no liquid below your eutectic point temperature, because remember what the definition of a eutectic point is. It's a minimum melting temperature. So uh, there there are there is a that's not a I should clarify that. Um, you can have eutectic points where you go from a solid phase to another solid phase, but in this specific case, we're talking about minimum melting temperature. So there's no liquid below your eutectic temperature. And CE, your eutectic composition, we should say, is C subscript E, and that's the composition at temperature TE. Your eutectic reaction is the liquid goes to the liquid with concentration E is interchangeable. That's what this little line means, that you can go up and down based on your temperature to your composition of E plus R composition R of E are, I think that these symbols didn't really turn out well. But essentially what this is referring to is that your liquid concentration comes down, and then it becomes part of this tie line here. So basically, once I go right below that eutectic temperature, I don't no longer have liquid, then I have to draw a tie line. And yeah, I have this concentration here going to beta, and I have a concentration here going to alpha. And I think that's what this is trying to say, but my symbols must have gotten messed up. Yeah, and here it is just a little better. So so right now we're at 71.9 weight percent silver. And based on whether we're heating it or cooling it up or above or below this eutectic point, we're going to go between our liquid to our alpha plus beta. And this will both be solid, by the way. This will go from a liquid to a straight solid. Okay, so for a 40 weight percent selenium, I think, 60 weight percent lead alloy at 150 degrees Celsius determine the phases present. Okay, so if I'm at here down here, if I look at my x-axis, I have my weight percent selenium. I hope that's what this is, because I don't remember what SN is, but I think it's selenium. We go from 0 to 100% in our concentration. We're at 40 weight percent selenium, so don't get confused by that, because you could just read this really quickly and say, oh, it's 60 weight percent, go with that. Well, that's wrong, because we're not talking about 60 weight percent lead, we're talking about 40 weight percent selenium. So we're actually 20, 40, 60 right about here. And they want to know the phases present at a temperature of 150 degrees Celsius. So this is a very low melting point alloy. So we're here at 150, and so that's our temperature. We draw our line straight over to 40 weight percent selenium, and we're at this point. So you can probably guess for yourself what phases are present. It's alpha plus beta. And here they go. Boop, boop. And they're going to say alpha plus beta. Yep. And, oh, whoops, going too far ahead. The phase compositions, we can figure that out pretty quickly. What we do is we draw our tie lines, R and S. One tie line goes all the way over to our beta phase. We draw it down, and we get 99, about 99 weight percent of our beta phase. And we draw our line to the left. We get about 11 weight percent of our alpha phase. So it's 11 weight percent selenium, 99 weight percent selenium, right? You always have to think about it in terms of whatever this x-axis is. And then the relative amount of each phase we can calculate using our weight, our mass fraction calculations from earlier. So that's just that same teeter-totter rule system, using those equations to calculate what our mass fractions are. So specifically, we're going to take 99 minus 40 for S, and then to get R plus S, which is just the full length of this line, you're going to get 99 minus 11. So it's 99 minus 40 over 99 minus 11 ends up being 59 over 88, 0.67 mass of selenium. And then if you want to get, or I'm sorry, mass of your alpha phase, sorry. And then if you want to get your mass of your beta phase, I mean, it's just the inverse, right? But you can calculate it using the teeter-totter rule, and you can go full out and get 0.33. Okay, here's another lead selenium eutectic system. And for the same, that's the same alloy at 220 degrees Celsius. So it's the same weight percent. So we're still at 40 here. But now we're all the way up at, let's see, let's do 100. So we're going to be like right here. We're in our liquid plus alpha, but oh so close to our liquid. So what we're going to do is we're going to draw that line there. We're going to get our tie line. But right now we have liquid plus alpha. They're going to ask us for our phase compositions, and here they are. We draw our tie line again. We get 17 weight percent selenium for our alpha phase, and we get 46 weight percent selenium for our liquid phase. And then if we want to get the mass or the relative amount or mass fraction, then all we do is we use our teeter-totter equations again, and that'll be just S, which is going to be 46 minus 40 over the full length of our line, which is going to be 46 minus 17. And then that ends up being 0.21. And then the inverse of that would be our mass fraction of our liquid phase, and that would be 0.79. So put another way, that means that 21% of the mass is alpha phase, and 79% of the liquid is liquid, or 79% of the mass is our liquid phase. Okay. Then we have microstructural developments in eutectic systems. So for alloys, at which your concentration is less than 2 weight percent selenium. So we're talking about little tiny. You'll notice that our alpha phase diagram has gotten a lot sharper, and Pikachu's ear is now much more horizontal than it was before. That's because we've zoomed in to this side of the graph. So at 2 weight percent selenium, the result at room temperature is going to be polycrystalline with grains of alpha phase having composition of C naught, which is right along this line, right? So we're at 2 weight percent selenium. We're going to have just one composition. And I think we're measuring, let's see, at room temperature, it's going to be 20 degrees Celsius. It's going to be about like here-ish, right there. So I guess if we're cooling it from above this temperature, we're going to start with our molten liquid. Once we pass through this area, we're going to have liquid and alpha. Then we're only going to have alpha. Yep. Now we have alpha. And then once we cool it enough, what it looks like will happen, if I'm right, is we're only going to have alpha and beta. So we're actually going to have a solid transition, phase transition from just alpha to alpha plus beta. And they don't show that. And result is temperatures in, hold on a minute. That's okay. So this will be the second part. So for alloys for which 2 weight percent selenium is less, okay, so between 2 and 18.3 weight percent, we're going to have temperatures in alpha beta range. At these temperatures, we're going to have polycrystalline with alpha grains and small beta phase particles. Okay, so these are both going to be present, but the beta phase particles are going to be present inside of the alpha grains. So we're starting with a liquid. We're going to move down to our liquid plus our alpha grains that are starting to form. Then we have a pure solid now. It's going to be just alpha phase. Then once we go down here, we're going to start getting these little beta particles start to form inside of these alpha grains. And here they are. And they should start to get bigger as we go down because of the slope of this graph. And we don't get to see it. Okay, so for alloy of composition is equal to the eutectic composition. So right here. Eutectic microstructure or a lamellar structure of alternating layers will form. This is in steel, we call this perlite. And so for our lead selenium system, at our eutectic point, we're going to get these cool little patterns that form. Otherwise, what we end up getting is on the alpha side, we end up getting the same perlite structure that you would see here, but with additional alpha phase blobs or globules, as I call them. And then if we're on this side of the eutectic point, then we're going to have the same perlite structure, but with a beta phase globules. Think about it this way: your alpha and beta phases, they want to interact with one another, and they want to like uh, kind of layer up, right? But if you have too much of one, there's not enough of it to mix into the other, right? So they have to kind of form globules all by themselves. It's it's kind of like if you have oh, I don't know. Like let's say too much sandwich bread, right? But not enough sandwich meat, then eventually somebody's going to have to eat just a bread sandwich, right? Like it's not going to work. There's going to be too much of one than the other. So when you mix them together, you're not going to have enough of one of those, right? Unless you're at the eutectic point. And at the eutectic point, you have just enough of both. So we're going to start with liquid. And then once we go below that eutectic point, we now have our perlite structure. It's not really perlite for lead, selenium, but for steel, that's what we call it. And we can also get the weight percent of alpha phase and beta phase compositions in the structure, right? And here's a micrograph of that, which is really fun to look at. Looks kind of like a zebra pattern, but you can see you just have these little layers of alpha and beta phases kind of overlapping with one another. And we zoom in and look at it from a cross-sectional side. Like if I were to cut this guy in half and look at it from, let's see, like the textbook, if I hold the textbook up and I cut it in half and I look at the pages, right? That's kind of what I'm doing. You can actually see that these are growing outward like this, and they're just overlapping. So you have selenium, lead, selenium, lead, and it'll grow outward in a single direction. And here's your zebra. Okay, so uh, also for alloys in which you have 18.3 weight% selenium, so between 18.3% and 61.9%, so between these two regions here, you're going to have alpha phase particles and a eutectic microconstituent. So we get, or you get our globules that form, and just above our eutectic temperature, you're going to have liquid and alpha phases between this region. And you can calculate the mass fractions at each of these steps, just like we've talked about before. And you'll notice, you know, in some instances, you can actually get half and half, which is interesting. And here are those little globules that I'm talking about. So we've got our primary alpha and our eutectic alpha. So we're actually going to be differentiating between the two of those, right? So our eutectic alpha and our primary alpha have two different structures, two different microstructures. Our primary alpha is those globules. The eutectic alpha is the lamellar structures. I think laminar is actually the right term. I think that they have referred to it as lamellar. Is that right? Lamellar. I have heard the term laminar. So I wonder if those are synonyms or not. That's interesting. When you talk about composites, when you're in the world of like carbon fiber and stuff like that, when you have different like sheets of stuff glued on top of each other, it's referred to as a laminar structure. Okay, so and again, just above your eutectic temperature, you're going to have this mass fraction, but when you go below your eutectic temperature, what happens? You're going to have this structure, and you're going to have different weight percentages that you're going to have to talk about, right? Instead of talking about liquid, you're going to have to start talking about your beta phase, because that's what your liquid ends up becoming, is kind of the idea here. Okay, so we need to talk about the difference between hypoeutectic and hypereutectic. Hypoeutectic just means that in terms of concentration, you're below the eutectic point, so you're to the left of the eutectic point. Hyper-eutectic means you're to the right of the eutectic point. So it depends on how much concentration of selenium you have in this specific case. So boom, we got hypoeutectic. So here's our laminar structure with our blobs of alpha phase. And then on the other side, we've got our laminar structure with our blobs of beta phase. Right in the middle, we have our sweet spot where we have only our laminar structure or lamellar structure. Okay, so you can have intermetallic compounds. Intermetallic compounds, it's not really an area because of stoichiometry, which is the composition of a compound. It means that the composition of a compound is at a fixed value. Basically, what they're calling out here is that for magnesium, this looks like a, don't know how to say the full term, but like it's a magnesium lead compound. You can have a straight line which represents a specific type of material. And this is a much more complicated uh, phase diagram than we're used to. It does have a eutectic point, so it's a trying to figure out. So this is weight percent lead. The other side must be magnesium. So notice how on this one, the way we call it out is on this side you have magnesium, and on this side you have lead, just to show you it's a magnesium lead compound. But what will happen, it looks like in this case, instead of just having alpha and beta, you actually end up forming a bond between your magnesium and your lead at certain concentrations. And so this will just happen, naturally at certain concentrations, and this will form. So you can actually see, like if I'm molten magnesium and lead, in a slurry together, I can actually, if I have a low concentration, I can go down to alpha plus liquid, and then I can go into alpha, and then I can actually start forming my Mg2Pb, or my, I wish I knew what those, what is that, lead magnesite or something like that. You cool it down below this, and then you have your alpha phase plus this material that starts to form inside. And you'll actually see at room temperature, it always forms, right? So once you cool it down, you're always going to have your magnesium and lead a metallic bond, which is interesting. And so you can play around with it at different stages. Okay, so we're going to talk about the difference between the phrases that we use here: eutectic, eutectoid, and peritectic. The eutectic, at your eutectic point, as we've been talking about, liquid transforms to two solid phases, right? So we're going from Rl to alpha plus beta, for example. Eutectoid is one solid phase transforms to two other solid phases, okay? So this is kind of what we were talking about in last class. This is when we have our steel, for example, and we're going from gamma to our alpha phase. So what was gamma? If you said austenite, you're right. And then you're going into alpha. If you said perlite, I'm pretty sure you're right. And then you have Fe3C, which is cementite, they tell you. And then peritectic is when you have a liquid and one solid phase that transform to a second solid phase. Okay, so this can happen in certain situations. So for your iron carbon phase diagram at around 1500 degrees Celsius and 6.16 weight percent carbon, you have a situation like this where gamma will become a liquid and another phase, like a different phase. So this is like above that diamond shape on your iron carbon phase diagram. Okay, so copper zinc phase diagram. So here's a really complicated one, right? So this one's a way more crazy than what we're used to. Temperature only goes up to about 800 degrees Celsius, so we don't have liquid in all cases. We do have a pure liquid over on this region, right? And then on this region, we have our gamma, right? It's copper zinc, so it's definitely not steel. But in between, we have all these weird things that start to happen, right? So we can start up here at around fit. Let's say we're at, okay, so we're only going from 60 to 100. So let's say we're at 70 weight percent, and we're at around 700 degrees Celsius. So we've got some liquid with gamma phase particles mixing around in it. And when we start to allow that to cool to room temperature, it'll go down below this line. And then suddenly we're in a region of gamma plus delta, right? Gamma plus delta. And that will be, so that's a peritectic scenario where we're going from, oh, I'm sorry, it's not peritectic. We're going from a gamma in a liquid solution to gamma plus delta. And then as we cool down, we get gamma plus epsilon, right? So weird stuff starts to occur. If we go down here and then we start increasing the composition magically, I actually can't think of a practical way you would do it, but let's say you could. We start going to the right, we actually go into an only delta regime and then only delta plus liquid. Now, at any one of these stages, you can always draw a tie line. So that's something I want to make you aware of. Right now, we only have delta and liquid in this region, right? So if I draw a tie line at 80, let's say we're at 600 degrees Celsius and 80 weight percent zinc, my tie line will stretch to delta and stop, and then I'll draw it straight down. And then my delta will go to, or my other part of the tie line will go all the way to this liquidus line, and it would draw it straight down, and we get something like 87 or something. Yeah, and so we're pointing out eutectoid transfer. This is a eutectoid transformation where we're going from one phase to two phases. Peritectic happens when you go from a gamma phase plus your liquid to the delta region. And I guess we're not going to show off a eutectoid, but it's when one solid phase transformed to two other solid phases. Which, I mean, technically, that's what this looks like to me. Point E should be, yeah, eutectoid. That's right. So we did say that. Not eutectic, but eutectoid. It's two different ones. Okay, so here is our wonderful, beloved Pikachu with his arm outstretched iron carbon phase diagram. So on one side, we've got cementite, which is Fe3C. On the other side, we have pure iron, right? So what we're doing is we're adding carbon. But in this case, we're only going up to the feasible limit of steel, which is around 6.7 weight percent carbon. Beyond that, you get into really high carbon steels, and they're usually too brittle to be useful. I think cast iron is actually somewhere around there. A lot of people don't think of iron as being a steel, but technically speaking, it actually is. And that's why it's so incredibly brittle. So there are two important points to make. So we've got a eutectic point here at point A. And when we go from our liquid down, we get gamma, which is austenite, plus cementite below our eutectic point. We have a eutectoid here at the bottom of austenite, where we're going from one solid phase to two solid phases. So we're going from gamma to our alpha phase plus cementite. Gamma, gamma, gamma. And then we get this really fun needle-like structure with a cementite, which is really hard, and our alpha is our softer ferrite. It's called ferrite. And the result that we get here is pearlite. So alternating layers of alpha and cementite phases. So I should withdraw something that I said a little bit earlier, which was that our alpha phase is pearlite. It's not necessarily true. It's actually our alpha phase and cementite phases in that kind of structure that we saw before. So that cementite makes up part of this, right? So we have hypo-eutectoid steel, and you can probably guess that we also have hyper-eutectoid steel. So down at this region, we're going from gamma to our alpha. We actually first go into this region, and I'll give you a second to think about what this region here is, what phases are present where my little red dot is. And that is indeed alpha plus gamma phase. And then once we go below that, we actually get into our alpha plus cementite phase. Or I shouldn't say phase, region. Gamma, and then we start getting our little alpha seeds forming. Interestingly, we have the seeds forming right in the middle of our grain boundaries. to our different gamma grains. And then once we start getting down to this point, we have really large alpha phases growing. They're starting to eat away at the gamma phases. And then by this point, we're actually starting to grow cementite. So the gamma phase has now been entirely consumed, and we only have cementite and alpha. And this is cool. This is actually showing kind of like a difference between perlite and your pro-eutectoid ferrite. So in this region here, so you have these large pale regions, which are your pro-eutectoid ferrite, and then in the middle, you have your perlite, which is what we've seen before, right? This is actually two of these coexisting at once. Okay. And then we're just showing, you can always draw your tie line, right? If you need to know what the compositions of each of these are. And you're still going to follow what's on your concentrations down here. 0.76 weight percent for your gamma phase, right? And then on the other side, you're going to have a certain amount here. And we're going to get the mass fractions of each. And then down here, you'll notice that your tie line grows way long. And you can get the mass fractions of that using these equations. But they shouldn't be that different from the equations that we just discussed a little while ago. Notice you just take 1 minus whatever the mass fraction of this one is. Remember, I said you just take the inverse, and you'll find whatever it is you need. Not the inverse. I shouldn't say that. 1 minus whatever your mass fraction of alpha is will give you your mass fraction of gamma or your mass fraction of cementite here. Okay, so now we've got hyper eutectoid steel. And looking at this, now we're on the other end of our eutectoid, right? Now we're on this end. So we're going from our gamma down to where we're starting to get gamma plus cementite, cementite seeds that are forming. Now we're getting large gaps of cementite that are starting to consume the gamma particles. And now once we go below our eutectoid temperature, we start having perlite. Now notice the cementite lines that form here stay, actually. So you'll notice that. But now you start getting these alternating lines of cementite and your alpha phase, which is perlite. Okay, and then just showing that again, that we can do the tie lines, we can get our mass fractions of each quite simply, right? And then here you can actually see what they're trying to draw here, which is that you've got your pro-eutectoid your pro-eutectoid cementite lines here, and then in between you've got your perlite forming. Okay, so the eutectoid temperature changes with the weight percent of alloying elements. So once you start adding in like a bunch of different things to your steel or whatever, then your eutectoid will actually begin to change temperature. So if I add in 6 weight percent of nickel, it's going to drop my temperature, my eutectoid temperature by a certain amount. And the composition of the eutectoid also changes as you start alloying more elements, right? So like silicon, as you increase the amount of the weight percent of silicon in your steel, your concentration of the eutectoid is going to drop. And that will be it for today. So that is chapter 9. I recommend that you review this lecture. I'm going to be posting the slides as well. And the book is also very helpful with this. So as always, if you have any questions about any of these topics, feel free to reach out. And my office hours, I'm readily available at my office hours as well. Thank you.